Hello everyone, this is a video introduction to what we're going to do in lab the last 2 weeks of the semester. So we are going to look at AC circuits, and really what we're going to look at is trying to measure the functional dependence of capacitive reactance on capacitance and frequency of the driver, and we're going to do the same thing for inductors. We're going to try to measure the inductive reactance and see if it matches what we expect to get, do a little statistical analysis on it to see how likely it is to match what we were expecting to get, or to see what the difference is. So the write-ups out there, the handouts out there for you to look at. This is just a quick look at the setup in lab. So it's going to get a little bit weird as I move the camera around. Hello. As I move the camera around for you to be able to see some of the different things. Or maybe I'll keep the camera in place and pick things up. I don't know. We'll see what this looks like. So the first thing, your driver is this black box that's back here. So this is the frequency AC driver unit. I don't know if you can see the setup right there. The way it's set up right now is we've got it's set on, you can set triangle wave or sine wave. We've got it set up on sine wave. 1,000 hertz would be the frequency right there times this multiplier knob that's over here. And the multiplier knob is somewhere below 0.6. I don't know if you can see that. So we're expecting something in the neighborhood of 500 hertz from this driver the way it's set up right now. You can change it by moving these knobs across here, or by changing the fine-tuned dial over here. The amplitude is right here. We've got this thing pegged out, so it's giving us the highest amplitude, highest voltage driver that we can have right there. What we've done so far is we've got this vector board here, and we put a sense resistor. So this is a resistor that we're going to use to measure current in the circuit. And we have this thing in this first slot right here. You hook things up in these slots by pushing them down, the springs, and sliding the leads through the holes and pinching them back up. That's what we did here. We got the leads of the resistors through these holes back here. And so we got the resistor right here, and we've got hooked up across the resistor, we've got an oscilloscope. And so the oscilloscope's right here. That's all I'm going to do for you today, is to hook up this resistor and measure what we've got with the resistor. You will, after the resistor, you will hook in a capacitor or an inductor. You see an inductor right there. You got a box full of capacitors. There's more inductors up front. So you'll swap in different kinds of inductors or capacitors, run them across here. You'll put them in the circuit over here in the other slot, and then you'll have your circuit with a capacitor or an inductor in there. And you'll measure the potential. So what we're going to do, and the theory here is we're going to measure the potential difference across the resistor, use Ohm's law to use that to calculate the current that's in the circuit. We have a single branch circuit, so the current's the same everywhere in the circuit, no problems. And then we're going to measure the potential across the capacitor or the inductor and calculate the impedance from that. And we'll be talking about impedance in class on Friday more. We'll talk about it as the introduction to your lab talks about it. We'll talk about it more in lab on Thursday, but we're headed in that direction. So what I want you to see here, though, so that's the setup. You see how to hook things into the vector board. And I want you to begin the lab on Thursday just by playing with stuff. So I really want you to see the oscilloscope here. Let me toggle this so that I have the autofocus off, but I'm going to autofocus on so we can dig in just a little bit closer here. So anyway, this is your oscilloscope. And the oscilloscope is set over here. You can trigger it. So this is the trigger menu over here on this side of the oscilloscope. And if I turn this up, as I turn this thing up and down, this knob, you come back over here and you'll see that arrow right there is pointing to the trigger level. And so when the signal gets beyond that level, it will trigger, it will lock in and give you a trace on the oscilloscope like this. One of our goals for this week is just to get you to practice using the oscilloscope. So I'd like for you to run through, these are all different menus for running the oscilloscope, and I'm going to show you a couple of them right now, but I'd like you to play with them. The first thing you're going to do when you get in lab on Thursday is just what I've done right here. Hook up the AC driver to a resistor and a resistor only, and play with it on the oscilloscope. Get different traces on the oscilloscope right here. And you'll see the oscilloscope is telling you, here's the signal. That's the voltage across the resistor as a function of time. Voltage potential is a vertical axis. Time is the horizontal axis. You can change the vertical axis with this knob right here. So I can make the vertical axis more expanded, or I can make it blow the signal up. So that's the knob that changes the vertical axis. And you can change the time axis over here with this knob. So I can spread the signal out. Or I can see more peaks and valleys by changing the time axis across here. In the old days, when I was growing up, the oscilloscopes, you had to do all of the stuff manually to figure out. So if you wanted to know what the voltage across the resistor was, we call that peak-to-peak voltage right there. The half voltage would be half of that. Either one's going to work for you for what you want to do. But you had to measure that. You had cursors that you would move up and down and put a cursor here and a cursor here to measure that. And the same for the timing. You'd measure the time between successive peaks. And when you measured the time between successive peaks, you could then divide by that to get the frequency of the driver. You see that this oscilloscope's being very friendly in telling us this, all this information over here. It tells us we have a 312 millivolt peak-to-peak voltage and a frequency of 490.1 hertz, about 491 hertz. It's jumping around, so we would call that 491 hertz, basically, maybe 492. You watch that thing jump around and average it a little bit and say, okay, so that's about what we thought the frequency of the driver would be right there. If I move the trigger level, watch the arrow go up and down as I move the trigger level. I move the trigger level down below. We saw that before. Now it's down below the trigger level. You need a pulse that's bigger than what we have to trigger the oscilloscope. So the oscilloscope's not locking into it. You see the traces just dance across there. And I can move this up and down. Again, one of the things you want to do is play with that trigger level and play with your vertical scale and your horizontal scale on your oscilloscope to look at these different traces to make different, to see what it is you want to look at, to see the signal that's in there. You get a lot of information by looking at the signal and understanding what that signal is, so it's worth doing and reading this information off here. Let's go back and look at some of these knobs. If I push that knob, it says, okay, what source is channel 1, and what am I measuring? Frequency. I can toggle that to measure the period instead of the frequency. Sort of mean signal, peak-to-peak voltage signal, cycles, various things, minimum, maximum signal, the rise time, the fall time, position width, negative, just tons of stuff. We're back to frequency. So we're measuring frequency on that axis, okay? So that's good. Channel 2, channel 3, channel 4, channel 1, we got all of that stuff. Let's push this one right here. It says, do I want to measure the period there? What do I want to measure? Do I want to measure the peak-to-peak voltage? Again, you can choose whatever it is you want to show on these different slots of information that you have right here. Let's just leave it at that. Okay, so now I've got the rise time showing up there, the peak-to-peak voltage, the frequency. Again, just play with what you want that to be, and see if you can get different things that your different bits of information out there. So now I push frequency back up to that slot, and now I've got frequency in there twice, peak-to-peak voltage, RMS voltage down here in the root mean square. We'll talk more about the root mean square. So just try getting different bits of information. Try triggering different ways. You can move over and plug this into channel 2 and try triggering on channel 2 and doing different things here. Here's your trigger menu. So I get the trigger menu up there. It says it's an edge trigger. What happens if I push that? Video, okay, pulse, Okay, I like the edge trigger. Source channel 1. So I'm triggering on the signal coming in channel 1. I could move this to channel 2 and do everything in channel 2. And I'm triggering on a rising slope. When the rising slope gets above a certain threshold, it's going to trigger for me. So that says I probably want to move my trigger above here and to say, look, I want it to trigger when it gets above, it rises and gets above that level. I could make it on a descending slope. So falling slope, rising slope, mode. You play with that and see what it does. DC coupled or AC coupled probably doesn't matter for this experiment, and you can play with all of these different. You got a bunch of different things in there. AC coupling, DC coupling, noise reject, high frequency, low frequency reject. So different things that you can do right there to try to see what's going on with your oscilloscope. But again, we're going to use this oscilloscope. You're going to get the information that you're going to get out of here is to say, there you go. We got this thing locked back in, and to say the information that you're going to get out of here is going to tell you the voltage of the source and the voltage across the resistor is what we're measuring right now, and the frequency. So you're going to get this information out of the oscilloscope. The oscilloscope is set up to measure the voltage across the resistor that you see right there. You're going to put an inductor or a capacitor in the circuit right there, measure the voltage across the capacitor or the inductor with an external meter right here. You're going to want that external meter set to AC voltage like that, and that should give you all the information that you need in order to see the calculate the capacitive reactance and the inductive reactance, and to figure out their frequency dependence and their dependence on either the capacitance or the inductance. So I think that's what we got. I could stop rambling here. I'm just running out of new things to say. Play with the oscilloscope first with just the resistor in place like we're doing right here. Then start adding elements and playing with elements and try different combinations, try different capacitances and different inductances and a lot of different frequencies, and see if you can start to get that functional dependence, and if it's what you're going to expect it to be. We'll derive that in class on Friday, what the expectation value is. So that's what we got, AC circuits, capacitive reactance, inductive reactance. See you all later, everybody.